So let's look at the wave-particle duality of matter and energy. Now that seems like a pretty loaded term there. What we're just saying is that matter and energy both can have dual natures. They can act like a wave sometimes and act like a particle other times, which means that they're really some sort of a hybrid of the two, and that's not the way we're used to thinking about it, but we're going to show that that's the case. Now, we've started talking about light as being a wave, but we also saw that it's particle-like. That's a good start to this notion of a wave-particle duality. We started about that with energy, but it turns out matter, particles, atoms, baseballs, Earth, these things are also going to be wave-like, which is a really surprising result. In one of our other videos, we'll do some calculations where we see exactly how big of a wavelength some of these particles will have. Now, if I take a beam of particles and I start tossing it through a hole, it could be a baseball, it could be a photon acting like a particle, which we've already talked about. It could be something like an electron, or something like a neutron or a proton, or maybe it's just a beam of atoms. Turns out those are also going to act wave-like. If I put two beams of hydrogen atoms flying through here, they can also have interference patterns, and if we were to work it out, we'd find that this is going to be the wavelength for matter. The wavelength for matter, called the Broglie wavelength, is going to be equal to Planck's constant divided by the mass of that particle times its velocity. And notice, velocity is not going to be written as v. We're going to use a lowercase u because we want to keep it distinct from frequency and velocity. So frequency, velocity. Make sure that you're writing them differently, otherwise it'll bite you in some creative and innovative ways. Okay, now notice what that's telling us. If you have a really heavy object, that's going to make the mass large, that's going to make this whole fraction small, and it's going to give you a very small wavelength. Something like Earth should have a tiny wavelength. If you have something that's very light, it should have a pretty big wavelength. If you have something that's moving slowly, small number, the small number is telling us, okay, small number at the bottom, that makes this number large, large wavelength. So slow-moving things have a big wavelength. Fast-moving things are going to have a smaller wavelength. Big velocity, small divisor, we're going to have a small wavelength. From all that, we should have some intuitive idea of when the Broglie wavelength is going to matter. It's going to matter to us for fast-moving things and small things. Sounds like we're setting up the electron, doesn't it?